All right. All right, for this problem, it's going to be the same function. We're going to look at y equals 9 square root of 9 minus x squared. The idea here is to compare to the previous problem. So this one is going to be cylindrical shells. In the previous one, we did the washers method and discs when the lower radius is 0. You have the special case called discs. So in this case, we're going to look at the cylindrical shells. And so I want to highlight in this video the difference between when you use cylindrical shells and when you use washers or discs. Okay, so let's look at the geometry one more time. If you saw the last video recently, you will see that this will be very familiar, but just in case you haven't seen it. So this is actually, if we think of this as y equals square root of 9 minus x squared, if we square both sides and rearrange, you'd get x squared plus y squared is equal to 9. And so this is the circle centered at the origin with a radius of 3. But because we only have the positive square root, we're only looking at this semicircle. So we're really looking at something that looks sort of like this. Okay. So this is the region that we're interested in. And so our first axis of rotation is x equals 0, which is really x equals 0 here. And so we're really spinning this volume about the x-axis here. Okay. And so the points to notice here are, of course, the intercepts. And so we're going to consider, we're spinning about this, and so let's construct our rectangle. And if we did it this way, okay, and we're rotating this way, that's completely legitimate. And what we would do is we would get the same result. However, this method, when the rectangle you're looking at is perpendicular, so when area of rectangle is perpendicular to axis of rotation, okay, then that's washers. Okay, contrast that with, let's consider the one that we're trying to do for this example. We're going to construct our rectangle in this fashion, and so the rectangle, the area that's going to generate the rectangle, that is going to generate the volume as we rotate, is so when area is parallel to axis of rotation, okay, then it's cylindrical shells. Okay, that's a fine point that when I was in Calc, I remember being very confused about, and I had to draw little pictures and stuff like that. So I just want to be explicit. So if you notice that our area of the rectangle that we're rotating, this region around here is parallel to our axis of rotation, that's when you know that you're going to be using cylindrical shells. If we chose to do it this way, where our axis of rotation is perpendicular to our area, then we would be using washers or discs. Okay. All right, so let's go ahead and look at the volume then for the cylindrical shells. So we have the integral from a to b of 2 pi r, and I usually call it rho d something. Okay, so the rho is the perpendicular distance to axis of rotation, and this is the radius of the shell. Okay, or you might think of it as like the height of the shell. However you prefer to think about it. So those are synonymous in my book. Okay, so let's go ahead and carry out the calculation. Okay, so let's go ahead and finish calculating this up. So if we look at our geometry here, The perpendicular distance you're going to see here from the x-axis to this location is a distance of, so rho is equal to a negative x, since we're looking at it from here to here. Now, there's an interesting thing to point out here. Since we're considering the volume from -3 this way, once we get past 0, do you notice that we're starting to repeat? So in order to avoid a reddition or next over accounting for our volume, our limits of integration are actually going to be between -3 and 0, where this is x equals -3 and x equals 0. Because once we get past there, spinning this volume here is going to be already generated from over here. So we're going to have more volume than what we need. Okay, so our limits of integration are between -3 and 0. Our distance to the shell is -x, and our height of this rectangle is along this curve, and y equals 0. So it actually is just the function given. So our radius is going to equal 9 minus x squared. Okay, so plugging in all this information, we're going to get that the volume is equal to the integral from -3 to 0, going from here. There is no difference if you go from 0 to 3, in which case the only difference would be that your radius there would be positive. You wouldn't have to worry about the negative. I just drew it on the side since I already had that rectangle there. So, all right, so we have 2 pi. The height of the radius is 9 minus x squared. And then the perpendicular distance to the axis of rotation is -x dx. Okay, so there is our equation that will give us the volume. Now, multiplying through things and kind of just simplifying little things, we have 2 pi, moving those constants out, -3 to 0, x, actually, and then the negative, I'll keep it here for a second, square root of 9 minus x squared dx. Okay, so this negative, actually, we could see it disappearing by flipping the limits of integration, or I noticed that this is an x squared and this is a single x. This is one less than this x squared. So this is screaming for me to let u equal 9 minus x squared. That's the use of I'm going to make, and then du is equal to -2x dx. Now if you notice, I have a -x dx here and a -2. Actually, I have a -2x dx all right there, 2 -x dx. So that's all the du piece, and this part is the u. So the only thing left over is the pi and then what's under there. Okay, I also want to change the limits of integration now. So if I plug in -3 in here, I get -3 squared, which is positive 9, 9 minus 9, so the lower limit of integration is going to be 0, and then if I plug in 0 for here, I get 9 minus 0, so the upper limit of integration is 9. Okay, the pi from here stays out in front, and then everything else is sucked up under the du, so I'm going to let u to the 1/2, where I'm just plugging in u and rewriting the root here as a power, so I can use the power rule. Okay, so I'm going to add 1 to this exponent and then divide by it. So that gives me a 2/3 u to the 3/2, evaluated from 0 to 9. And then 2/3 9 to the 3/2 minus 0. Okay, so this is the square root of 9, which is 3, and then I'm going to cube 3 and then divide by 3. So 3 cubed is 27, divided by 3 is 18. Okay. All right, so this simplifies to 2 times 18 pi. Let me say that a different way. That's not right. So this, let me slow down just a sec. So 2/3. This is the square root of 9 is 3 to the 3rd power, and then I cancel one of those out, and so you get this is 3 squared times 2. There's a pi there. This is 9 times 2, which gives me that the total is 18 pi. Okay. I was jumping to the conclusion, and I saw a factor of 2 earlier, so sorry about that. Okay, so this is the volume then. So the volume is equal to 18 pi units cubed. And if you think back, this is a sphere, and we saw in the previous video that the total sphere, when we rotated about the x-axis, gives a volume of twice this amount. And since we're rotating about the y-axis, we're only getting half of the volume of the sphere. So it makes sense that we would get half of 36, which is 18 pi cubic units. So the volume checks out from our previous examples of what we would expect. Okay, and so now let's move our axis of rotation from this vertical axis of x equals 0 out here to x equals 5 and see what happens there. Okay, so here's the basic geometric setup. So our function here is the square root of 9 minus x squared, and we're rotating it about the line x equals 5 here. Okay, so if I can construct my geometry here, here's the rectangle that I'm going to be rotating about the line here. And so you can kind of see the cylindrical shell that it's pointing out. And so here is the perpendicular distance that we're going to be rotating through. Okay. Okay. All right, so to figure out the distance, the perpendicular distance, we notice that this value here is x, and so any point along this line between, so if I'm here, from here, from here, it's going to be the distance of 5 minus whatever this length is, okay? So rho is going to be 5 minus x, and that'll give you the perpendicular distance to the axis of rotation. Okay, likewise, the height of this curve, okay, the height of our radius, here or here, is going to be given by the same function, 9 minus x squared. Okay, so the last thing we need to do is determine the limits of integration, and so there's nothing stopping us from repeating all values from -3 to 3. So the limits of integration are actually going to be over the entire domain of the semicircle. Okay, so volume is equal to the integral from -3 to 3. We have 2 pi. The radius is 9 minus x squared, the height of it, and then we have 5 minus x dx is the perpendicular distance between the axis of rotation and the arbitrary place of our area being rotated. Okay, all right, so the next thing you should know is that I can distribute this quantity into each of these two terms, and that's going to help create some simplifications in the calculations that we need to do. So I'm going to go ahead and expand this. I'm going to distribute this term into each of these and write it as two separate integrals. So the volume of -3 to 3 of 2 pi square roots of 9 minus x squared. I'm going to multiply that by 5 dx, and so that's the first distribution. Then I'm subtracting the minus coming from there. Then I go from -3 to 3 of 2 pi, and then the square root of 9 minus x squared times x dx. Okay? All right, so something to note here. If I clean up the constants and kind of move everything out, this is going to be 10 pi, the integral from -3 to 3, the integral of 9 minus x squared dx. Okay, and then I'll kind of do the same thing here. 2 pi, the integral from -3 to 3 square root of 9 minus x squared. And then I have an x floating out in front here, dx. Okay? All right, so some nice things to kind of notice here. Right now, we actually in class haven't figured out how to integrate an integral like this. And so we run into a problem of how do we do that with the skills that we have. Now, it should be obvious that what we actually have here is from -3 to 3, we have the area of a circle. So this is really just figuring out half the area of a circle, which we know how to do from elementary geometry, right? The area of a circle we know is pi r squared. The radius for us is 3, and then we're going to take half of that length. So this is the same thing as pi. The radius is 3 squared divided by 2. Okay, so this is 9 pi over 2. We multiply that by the 10 pi. Okay, so the pi, we're going to multiply that term there, and so we're going to get the 10 is going to cancel with the 5, or with the 2, giving us 5 pi times 9, so 45. 9 times 5, 45 pi. Okay, so that's the area of this one. And then let's consider the area of this one. Well, this may not look like it, but this we actually just calculated last time. We found that that was equal to 18 pi. Okay, so we don't have to go through that integration. We can make the u sub and all that. The thing I think I will point out is if we integrate it as is and we make the u sub, this is going to integrate to negative 3 to 3 with the u sub, u equals 9 minus x squared. If you plug in this, you're going to get that u is equal to 0 and 0, which produces an integral from 0 to 0, which is 0. And so we have to take twice that amount. So this 2 actually comes out as part of the doubling the integral. So using the symmetry, we can take this integral to be from 0 to 3. Removing the 2, we get 0 to pi is equal to the integral from 0 to 3 of x square roots of 9 minus x squared. And the minus sign coming from here, dx. And so this is actually equal to exactly the amount of the area of the previous formula. And so that comes out to be 18 pi. Okay? So we can subtract from this 18 pi. And so without having to do the actual integrations here, we get that the difference between 45 and 18, well, let's find out what is that. I can subtract directly, or I can say, oh no, look, this is 45 minus 20, which is 25 pi, and then I need to count up 2 more, so 27 plus 2. Okay, so this is going to be a total of 27 pi volume units cubed. Okay, and so that is the new volume of this shape rotated around this axis at x equals 5. All right, I hope that was helpful, and I'll see you in the next video.